Jnanam paramam dhyayam. Knowledge is supreme.
Let's now move on to tutorial 4, which consists of again 5 problems that will be divided into 2 parts, and just a recap of our previous journey in which we have discussed problem based on particle in a box. Then we had seen problems like to calculate the energy eigenvalue, energy eigenfunction, etc. And these problems will again, we will have such problems wherein you have to calculate energy eigenvalue and energy eigenfunction of an Hamiltonian operator. So, from wave function formalism, let us now move on to Bra-and-Ket notation, and in that you will see that we have already seen actually the in linear vector space, we have seen the how to calculate norm, how to calculate some inequalities we have learnt, like what Schwarz inequality, triangle inequality, and now we will slowly move on to the Bra-and-Ket notation, and let us get started with the problems. So, the first problem is you will see in after the result that this particular operator which is given to you, a cap minus I a upon a s minus I a I, is a special operator. After solving this, you will come to know what I am talking about. So, in the first problem, you are consider a ket space spanned by a eigenket a I is given and of Hermitian operator A. So, operator A is Hermitian. We know what is a Hermitian operator. A dagger is A, is what is Hermitian operator. Remember this, we have seen it before, but just to stress on, I am writing here, and we will be using this property if required. The next thing is that this Hermitian operator has eigenvalue a I. So, a I is the eigenvalue of this operator. So, you have to tell what is the significance of this given operator I going from 1 to n, a minus a I upon a s minus a I. So, this is a operator given to you, and in the problem this product notation is, so let me write this here, where I is not equal to s. This is what the question means. So, in the question you have seen I is equal to 1 to s, then s plus 1 to n. Okay. So, I is not equal to s, it is between 1 and n, excluding the value of s, that is what is given to you. So, now let us write this operator. You will operate this operator on a ket, that is the eigenket a I given to you. Okay. So, eigenket a I is operated on, so you have I is 1 to n, let me write this notation, a minus a I upon a s minus a I, operated on the operator a I. Okay. And here you must note that a I is the eigenvalue of this operator. So, let me write here, when a is operated on the eigenket a I, you get eigenvalue a I Okay, this is the eigen operator or the eigenvector, sorry, this is the operator and this is the eigenvalue. So, now when you operate this I equals 1 to n and I is not equal to s. Okay. So, A minus Ai upon As minus Ai, this is the operator. Now, I will operate a eigenket Aj on this operator. Okay. So, when Ai is operated on A, you get Ai, and now when I operate Aj on this, what do I get is Aj minus Ai upon As minus Ai. This is what you get when Aj is operated on this. Okay. Now, you can see that from this, can you make any conclusion? No. So, you have to see case by case. So, in case 1, okay, there will be 2 cases. So, case 1, when j is equal to I, okay, j is equal to s, sorry, when j is equal to s. So, from this what do you infer? Okay, and of course, this sum the product is there, this is there, okay. And now when j is equal to I, what do you obtain? When j is equal to I, you get the right hand side becomes 1, the eigenvalue becomes 1. So, eigenvalue is 1, okay. And when j is not equal to s, so when j is not equal to s, this is not equal, but I goes from 1 to n, and if it picks a value when j becomes equal to I at some point, the numerator becomes 0. So, at least one value is 0, okay. At least one eigenvalue is 0, okay. That means for j not equal to s, the eigenvalue becomes 0. So, this operator is simply written as, this can be written as S, okay. So, this is nothing but your projection operator, okay. Remember, the projection operator is when S are same. So, you can really write this when you operate this operator on J, operator A minus AI, As minus Aj, this when operated on Aj would give, now in terms of this S operator, when you write, okay, or the jth operator you will obtain, okay. So, in terms when S is equal to j, so let me write this as As rather. So, when S is equal to j, you will have just Aj. So, when this is 1, you have when j is equal to s, and when j is not equal to s, this one will become 0. So, now let us go to the second problem. Now, in problem 2, this is an exercise for you to get hands on Bra and Ket notation. So, Bra and Ket notation you have to use to calculate that the trace of x and y is equal to trace of y into x. So, this is what we have to prove. Trace of x times y is equal to trace of y times x. This is what we have to prove. So, in this we will use Bra and Ket notation. So, what is trace basically? It is sum of the diagonal elements. So, now this trace in Bra and Ket notation can be written as x, y, n. So, when you are multiplying, when you write this operators and do product, and once you get the product you add up the diagonal element. So, you will add up, this will be sum over n. So, when you sum up the nth element, so this is your x times y and you will sum up the diagonal elements. You will do this sum when n is equal to n. That means the Bra and Ket part of it is same. So, 1 1, 2 2, 3 3, n n and so on, you will add the elements. So, now this is n, and in this I put a projection operator, a complete eigen ket m. So, let us assume that m, this is y, okay. This is, you can write this as summation over m n, and you can write this in the Bra and Ket notation like this. So, in the next step what do I do is I can actually flip this, because this is a multiplication. So, it will not matter if I just flip these dummy indices. This is now the projection operator, which is 1. Okay. I can again write this as m trace of x and y will become now y times x m. Okay. So, in the previous you have seen that you have m, y and x. So, now this will be nothing but this trace I can rewrite again as trace of y times x. Okay. So, this is very simple exercise, and it is expected that you in order to get hands on Bra and Ket notation, you must do such simple exercises, and even in coming problems we will see that using Bra and Ket notation it is very simple to solve the problems. Let us go to the next simple problem, which is given to you that an observable A has eigenstates 1 and 2. Observable A is given to you which has eigenstates 1 and 2, and the Hamiltonian operator. So, the eigenstates of this operator are 1, 2, and the Hamiltonian operator is given by something like this is given to you. Now, this can be written as, this Bra and Ket notation can be rewritten as the matrix form. You can write this in the matrix form, where omega is a constant and you have to derive the eigenstate and their eigenvalues. Okay. So, here we have omega. So, you have 1, 2. So, when you are writing a matrix, this will be 1 1 component, this will be 2 2 component, 1 2 will be here 1 and 2 1 will be here 1, and 1 1 component and 2 2 component are not given. So, this is the way you will write. So, you can see in the previous tutorial also we have seen such problems. So, going further to the next part of this problem, where you have to calculate the eigenstate and the eigenvalue. You can see from this Hamiltonian operator and guess the eigenvalues. It is very simple. So, you remember the eigenvalue equation. Okay. So, those who do not know how to calculate, let me demonstrate again. Okay. This is the eigenvalue equation. Operator H on the eigenvector on a vector psi 1 is equal to lambda is the eigenvalue and psi 1 is the again the eigenvector. So, once you want to calculate, once you calculate the eigenvalues, you can easily calculate the eigenfunction. So, from this I can say that the eigenvalues are omega and minus omega. It is very simple. You have to just substitute for the Hamiltonian and Hamiltonian operator and calculate the corresponding eigenvalues. Then what you have is, so if I call lambda 1 is omega 1, okay, then I will have operator H psi 1 is equal to lambda 1 is omega and lambda 2 is minus omega. So, H operator on psi 1 is omega psi 1. Then you know now what is operator H, omega psi 1. Okay. Then you can simply know from here. So, when I do this, I have a psi 1 here. Okay. Let me write psi 1 as some x1 x2. Okay. Then what do I get here is x2 x1 is equal to x1 x2. Okay. Simply then let me do it here only. So, x1 is equal to x2. This would imply that you have psi 1 is 1 by root 2 1 1. It is very simple to see that your psi 1 is nothing but 1 1. So, how do I get the values of x here? Again I will use the normalization condition. Psi 1 star psi is 1, then you find out the normalization factor and then you calculate this. Now, again this is for psi 2, let me call psi 2 as x2, some y1 and y2. Okay. So, for that same way, when you substitute for psi 2, your lambda 2 is minus omega. So, you will have x2 as minus x1 and x1 as minus x2. So, if your x1 is 1, then your x2 is minus 1. So, your psi 2 will be 1 by root 2 1 minus 1. Okay. This is the way you can write. Now, again I have to rewrite this in terms of 1 and 2 operator. This eigenvector I can write in terms of the eigenstates 1 and 2. How can I do that? This is again a simple step wherein you will write this. Let me demonstrate for one. The second one you can easily calculate. Psi 1 we have got, this I can rewrite it as 1 0 plus 0 1, correct. So, now this is 1 plus 2. Same way psi 2 you will get something like this. So, now you have expressed the eigenstates in terms of the states 1 and 2. So, you have psi 1 as this, psi 2 as this, and this corresponds to eigenvalue omega, this corresponds to eigenvalue minus omega. It is a simple way of doing. So, if you have not done such examples wherein you have to calculate the energy eigenvalues or eigenvectors, this exercise is a must for you. This is a simple example and that will help you to solve more difficult or different problems. So, you must try at least one such problems. In the next part of the tutorial, we will have 2 more problems. Let us meet in the second part of the tutorial.